Okay, so the goal for the course today, after having clarified all the introductory material, is actually to stimulate your interest in photogrammetry. So we will not go into a lot of technical details today, but I just would like to give you a very, very brief introduction to some basic techniques, or some basic principles, not even techniques, and then show applications. So you'll see a couple of nice images, nice videos today, just to stimulate your interest. And that's kind of my goal for today. And the first question to answer is actually, what is photogrammetry, or where does the word come from? It's a Greek word, and it has something to do with light, photo light, and it has something to do with measuring. And the most simple way is we measure with light, especially with photographs. So we basically take pictures of a scene, of objects, and want to measure with that, or to interpret the data that we have. Interpretation can be done on a geometrical scale. That means we want to estimate the geometry of the object that we see. But it can also mean a semantic interpretation. So we want to identify what we actually see there, so that some box-like object that we see is actually not just a stupid box, but it's, for example, a car or a building. This is kind of the idea of semantic. So we want to understand what we actually see or analyze the scene. So if you look to the definitions, one of the definitions we find about photogrammetry, it's the estimation of the geometric and semantic properties of objects based on images or observations from similar sensors. We said, okay, geometry should be pretty clear. Semantic, maybe not perfectly clear yet, but simply see that as names. So we can give names to objects, like car, building. This is something we can see as a semantic interpretation. We have objects, that's pretty clear. We have images, we have more camera, or observations from similar sensors. That's actually where it starts. So the first question is, what could be similar sensors? Any ideas? Radar, yeah, maybe something, although this is often not in the center of photogrammetry, but it's definitely possible. We can also use satellites. We can put a camera on a satellite. We also can use other electromagnetic radiation to do that. That's also part of you can even argue if is remote sensing, where what this would refer to, or Fernerkundung, part of photogrammetry or the other way around. Depending how you see that. So photogrammetry is typically older than remote sensing, so it started as a subdiscipline in remote sensing. If you generally say remote sensing is something where you sense something without contact, you can even say that everything which is done in photogrammetry is part of remote sensing. So question how you define that. What other things you can think of, which is actually things that are very similar to cameras, standard cameras?
Laser scanning?
Laser scanning is definitely something which is part of photogrammetry. So where you have like a laser that I have here, and what the laser scanner basically does, it emits a laser signal. The signal is reflected from that wall, and it simply measures the time it takes for the light to travel to the object and to travel back to a sensor in here, and then it can actually calculate the distance. What else do we have?
Infrared sensors.
Infrared is also definitely something very similar to cameras. Even sensors which have cameras and in infrared. They can perceive infrared light, that we can actually get multiple channels. Anything else? Think about your mobile phone. What makes your mobile phone special? It can record videos. So videos are basically streams of individual images which are taken one after the other with whatever, 25 frames per second or 30 frames per second or even more. So we get multiple observations of the same scene, so we can actually exploit that. For example, if we have a still scene and the camera doesn't move, we take multiple images. We can actually combine those images to increase the quality of the images. Or we can actually move the camera and get multiple images of the same scene from slightly different viewpoints. And this allows us, for example, to estimate 3D geometry or estimate changes over time in a scene. These are all things that we can actually use for video cameras or smartphones. Smartphones may have other sensors as well. Typically, you have an inertial measurement unit in there. which tells you something about your attitude, gives you information about your attitude quite well. You can actually exploit that in the estimation processes. So all this can be seen as part of photogrammetry, although traditional cameras are kind of in the main focus, at least of this course here today. So next question is, what do we actually measure? One thing we often start with is a camera orientation. So where is the camera and where is the camera actually looking to? This was the example that I had before. I just stand here and take a picture of you in this lecture hall. And later on I have that picture, I want to know from which location has this image actually been taken. Can I actually do that? And if I know something about the scene, or at least I have some information about the scene or the geometry of the scene, I actually can do that. I can actually estimate the position where this camera has been taken to. If I know different camera locations where images have been taken, I can also infer something about the geometry of the scene by once taking a picture of a person sitting there in the back from this location, and from this location I can actually, via triangulation, estimate how far that person is away. So it allows me to get some information about the location of the object or a 3D reconstruction of the scene or of the objects. If I want to have a full 3D reconstruction, I may need to make sure I observe the object from all sides, and I observe everything which is relevant. There are no occlusions. These are all things I need to take into account. At some point in time, I even want to maybe recognize an object. So not that this is one person, but this is a specific person. Or I want to do an interpretation of the scene. So if I have a scene, I can actually generate a description which tells me what's going on. So if I see, for example, people walking into a building, is the system actually able not to just say people and building, but actually can generate a story out of that? There are people entering that building, for example. So this is important for a lot of things where we want to monitor tasks and want to get interpretation of the scenes. Or very popular at the moment is things in the context of autonomous driving. So we have cars which actually can drive autonomously, but these cars actually need to understand what's going on in front of the scene. So the classical example is if you have kids playing on the sidewalk, is there a risk that this person actually enters the street? In order to answer that question, you need to understand what's actually going on in that scene. And therefore, this automatic scene interpretation is something which becomes more and more important, especially if we think about applications where things move, especially heavy things move, like a car, can actually harm people. Also, photogrammetry is not a field on its own. So there are actually several different disciplines which have a very, very substantial overlap with photogrammetry, maybe come from a different background. So two of the things which are important for understanding what's going on the figure, actually, they have something about object, about the 3D world. And we have images. So one of the things is if I say, okay, if I know what the object looks like, and I would like to know what the image looks like, you can see there's this arrow over here. And this is something which computer graphics people do. So you have a CAD model, for example, of an object, and you actually want to render a photorealistic scene. Or if you want to render movies, that's a task that you're doing. You're going from an object description to an image. This is also the process where you can see if you take your camera and take a picture, physics is doing that job for you. But if you want to understand how that's going on, that's something you find in computer graphics. In photogrammetry or in computer vision, you're typically more concerned with the task we have an image, want to actually get some information about the object. So this process of having images and inferring something about the scene. This is something which is, again, photogrammetry was one of the first disciplines addressing this problem. Over the last 20 years, the community in computer vision, which is a branch which typically started from computer science or from electrical engineering, is actually solving very, very similar tasks, maybe in a slightly different objective function, not always measuring per se, but scene interpretation, change detection, analyzing what's going on. These are also very, very core fields of computer vision. And actually, the computer vision community is very large compared to the photogrammetric community because it grew dramatically over the last 30 years. So a lot of the developments in photogrammetry are nowadays influenced by things from computer vision, and a lot of people are actually involved in both disciplines. Also, remote sensing, I already mentioned that before. If you just say remote in the sense of not touching something, we can actually say photogrammetry is remote sensing because we take a camera, we measure a scene, and we don't touch that scene because we are apart from that. What we today describe as remote sensing more often is actually remote sensing from very far apart. So if you have cameras or other sensors in the context of measuring electromagnetic radiation or emitting that on satellites, we are actually very far remote. We are observing objects on the Earth. And we can see that if you see this kind of from the task description or from the historically development, we may end up saying one is inside the other or the other way around. Also, robotics is actually a pretty young discipline, actually a discipline where I come from originally, is concerned with the problem of understanding what's going on, measuring what's going on, building maps of the environment, localizing in those maps, interpreting the scene. So everything which happens at the moment in the context of autonomous driving is actually part of this robotics movement. It's also very important there, exactly the same problems. What does the environment look like? Where are we? How can we describe the scene? What is important in the scene? What do we need to take care of for a given application? And that's also a very important part. And all these fields actually come closer and closer together. Started, for example, if you look to these autonomous UAVs, so unmanned aerial vehicles, these small drones that you can buy for, whatever, 1,000 euros with cameras equipped on that. Something which was very popular in robotics and now is one of the standard tools also for in geodesy for actually measuring objects, fly to very hard to access areas. There are a lot of overlaps between those areas here. Robotics is also concerned with actually manipulating the world. So we want to change something about objects. That's not that relevant in photogrammetry. And we have this aspect here of actually changing something in the image, is also called image processing. This is still relevant for photogrammetric applications because we, for example, want to improve images, change the contrast in images, or doing some manipulations, normalize images under certain conditions so that we can actually perform then a better interpretation about what we see in the world. A little bit in the context of connections or also historical connections between those disciplines. So photogrammetry developed as a part of the geodetic sciences by using cameras or images, analog cameras. Actually, you see a lot of them in the back there. There's a lot of old aerial cameras or cameras used for doing measurements, building maps of the Himalaya, using those cameras in order to observe the Earth, build maps, and estimating, doing state estimation in this context. Also, as I said, remote sensing, or it's a special form of remote sensing, optical remote sensing. We're mainly concerned with optical sensors. And especially since the use of computers in photogrammetry, there's a strong link between image processing, computer vision, and photogrammetry. And last but not least, especially the aspect of state estimation robotics is very, very closely related to photogrammetry. So the question now, what are the advantages of using photogrammetric techniques? The first thing I said before is the contact-free sensing. So we don't need to touch the object. Why may it be an advantage to do contact-free sensing? Any ideas? Why is it a good idea to do contact-free sensing? Yeah?
Ja, wenn man mit dem Auto, also ja, ich meine, es wäre nicht gut, wenn ich jetzt den Fußgänger erst berühren muss, um zu erkennen, dass
Perfectly fine. I may destroy the object that I actually want to measure. That would be actually a very bad idea. What else?
It's far away.
It's things that are far away or inaccessible. They may be visible but inaccessible for us. So for example, if we are standing on a mountain and we want to build a map for the mountains on the other side, but we can't actually access that, that's a very good example for that.
It would be dangerous to get near to the object, for
Yeah.
example, when it's a volcano.
Yeah, or toxic materials in general, or very hot or very cold materials, also something which can be of relevance. Yeah.
If the object is too small to touch.
Yep. So definitely, if something is very, very small, maybe easier to handle that with a camera or very sensitive material. So these are kind of the main advantages of this contact-free sensing, which even pointed out more. That's great. The other thing why this is nice is actually that we can cover large areas quite easily. So if you would have to measure every individual point in a scene manually, that would actually be a very time-consuming process. With cameras, you have the chance, even video cameras, which take a lot of pictures in a sequence, you can actually acquire this data very, very easily. And you actually get a dense coverage of the scene if you do that, do the job well. Of course, you need to make sure that there are no occlusions, or you can handle occlusions, or observe objects from different directions. But in general, it's quite easy to handle this. The other thing is actually flexibility in terms of the resolution that I want to cover. So I can either go very far away from an object, so I have a coarse resolution but a large scene, or I can go very, very close and get a quite detailed view of what I see, but then cover only a small area. And I have all this flexibility within the process without, at least the algorithms not caring, so we may choose a slightly different hardware, but the algorithms for processing this data, it doesn't make any difference. We can actually do 2D sensing and 3D sensing. So one of the things is, if I take an image of a scene, I actually project a 3D scene to a 2D world. That's a problem from which you will suffer in the next year. So actually, you lose information, you lose the depth information if you project the 3D world on a 2D image plane. But if you take multiples of those images, we can actually try to reconstruct the 3D geometry of the scene. We can't do it with a single image, but we can do that with multiple images. It allows us to do 2D sensing activities and even 3D sensing activities if we have, at least if we have multiple images. There are a couple of other really important things. Dynamics can be actually recorded quite easily. So if I take whatever, an image every hour of a scene, I can actually try to estimate what changes in the scene. If I monitor the construction site, like the construction site outdoor there where the new building is built, if I take a picture every day, I can actually document the process of changes over time. We said before, we can actually interpret or perform interpretations using classification techniques, estimate semantics from this image data. And one of the things which actually is often forgotten, this is actually data which can directly be interpreted by humans. So we can just look to images and we have a pretty good understanding what's going on, at least for a lot of applications, and we can check very easily, is this data actually fitting my needs or not? Which is much more tricky if you think about, even if you think about laser range data. So you actually get range data, you get just distances of points. They're much harder to interpret as images. So it's actually very, very nice. Also that the images itself actually document the measurement process. So by taking multiple images and, for example, doing a 3D reconstruction of the scene, I can always go back to the original images. And if I made a mistake, for example, in the alignment of the images, I can actually go back to the original data and reprocess this data. Also something which is a big advantage, especially if it's very hard to obtain the data, or I have only one chance to obtain the data, and maybe I made a mistake in the measuring process, I can often recover that by going back to the original images. Especially since cameras are used for a lot of different applications. Cameras are comparably cheap because we have, every one of us has a cell phone with a camera, nearly every one of us. So cameras are a mass product. And this makes them actually very comparably cheap compared to, for example, other sensors. You can do real-time processing nowadays, or even fully automatic data processing. So this is all great. These are all nice advantages which I can use for these photogrammetric techniques. However, there's no free lunch. Whenever there's an advantage, there's also a disadvantage. So the question is, what do I lose? The first important thing is we actually need light. Sounds trivial, but if I want to monitor a process 24 hours a day and 12 hours a day it's night, I actually can measure only at 50% of the time if I can't employ an artificial light source. So light is needed, which can be a real disadvantage. Depending on the application that you have, this can be a limiting factor. You also need to take care about occlusions. So one object occluding another object that you can't see it, which can actually make all the measurement process quite hard. There are other sensing modalities like radar was one example. I can actually look through at least some materials and see behind the material. This makes things much easier. This point over here, you will struggle with that, I'm pretty sure, within this year, or especially in Photogrammetry II, is I lose information if I go from the 3D world to the 2D world. Because the projection, I'm basically losing one dimension. If I just consider one single image, I don't know how far the objects are away. If I know something about the size of the objects, I may estimate that. But it could be that there's just a very small toy car being very close to the camera, or a real large car being further away, for example. I can't estimate that distance, at least from a single image. If you have multiple images, we can actually do a better job in here. And there also may be other techniques which are actually more accurate than photogrammetric techniques. Also in terms of the relative precision, we can actually, so this is actually an advantage or a disadvantage. So I have a relative precision, or Relativgenauigkeit, and I'm always kind of in that area over here. If I do microscopy, I can actually investigate very, very small objects. If I go to traditional photogrammetric techniques ranging, let's say, from millimeters or centimeters, let's say tens or hundreds of meters, or if I go to remote sensing applications where I cover areas of kilometers or square kilometers of size. And depending on the camera setup that I have a certain relative precision always being in this area over here. But the nice thing is I can actually span a very large range of different scales I can actually address. So that's actually a nice property. Although there are techniques which may be more precise than those photogrammetric techniques. And one of the things already mentioned that cameras actually measure directions. So if this is a real 3D world, this should be the projection center of my camera. It actually generates an image which is upside down. And what the camera basically does, every of these pixels here in this image corresponds to a ray that goes through the 3D world. So every point which lies on that green ray will actually be mapped to this pixel. So if there's an object here and here, let's say a bird flying through the scene, it will map the bird, simply the closest one. And I have no idea if this is the bird here, an object over here, or the top of the mountain. So cameras are just devices which measure directions. Nothing else. However, if we take now two images, and I know from which locations these images have been taken, let's say one camera sits here, and one camera sits here, and I know the correspondences. So I know that this point in this image actually corresponds to this point in this image. Same holds for the other one as well. I can actually estimate where they lie in the 3D world by just, in the most trivial case, by just intersecting those two rays. So I take this ray over here and this ray over here, and where they intersect, that's actually the 3D location of the point. But what I need to know in order to do that, I need to know those points. You can also estimate them as well, but there's some information we still cannot estimate if we do that. And we need to know those corresponding points. We need to know that this pixel actually corresponds to the same object that I pictured, like this one and this object. So I need to take care to have those correspondences. And estimating those correspondences can be tricky. Okay, in terms of the basic principle, what lies behind that? So we have a contact-free measurement, and what we basically do, we measure intensities of photons. Photons kind of the smallest quantity of light. And what we basically measure is the intensities, which are basically counting photons of a given wavelength. In this, we will go into the details during this course. And this, what basically every pixel in your camera does, it basically counts the number of photons that this small sensor detects in a given time frame. And this gives you the intensity. And either you use the full spectrum, so that your sensor chip actually detects photons corresponding to different wavelengths, and you have, for example, a grayscale image, or you just say, I only want to have the red ones on this pixel, and I only want to have the green ones on this pixel. And by doing this, you can actually generate color images by then mixing those colors again. In terms of the geometry, we typically assume a pinhole camera model. So most of you probably have heard that. We have our scene. Let's say this example with the tree over here. We have a camera where we picture those scene. So there's one pinhole. You can see this as a camera, as a box with a single, very, very small hole in there. And let's say this is my box. And this is my image plane over here. And every ray from the world passes through this pinhole. Get those points over here. So what I see actually is get the tree upside down in here. And the thing is that, oh, sorry, they don't intersect here. That was wrong. Should be like this. It's not my camera. Everything goes through this single point. This is something what's often called a pinhole model or pinhole camera model. Okay, if we now look to the physics process of getting images, what we have is typically we have a scene with objects, geometries, types, and we have a camera, and we may know some parameters of that camera, like the focal length, and we know where this camera is, the extrinsic parameters. And putting those two things together, physics actually generates an image for us. There's actually this process over here. So this is the process of taking the measurements. We are now interested in having those images and actually going back to the objects or to the camera location. So we are interested actually in the inverted mapping. We start with the images. We know something about physics, so we can exploit that. So we can exploit that we know that we have that principle over here. We may have some additional background knowledge which we may exploit. For example, in the terms of classification or the semantic analysis I said before. I may have hundreds or thousands or millions of training examples. I can analyze that, and then can I say something about the object that I see and some of those parameters, like what type it is. And I can also infer something about the camera and then the parameters, so where that camera actually is. These are tasks. This inverted mapping is something we actually deal with quite often or actually doing this inverse mapping are most of the tasks that we actually do in photogrammetry. And all these tasks, actually the whole lecture actually can be explained with that. So we will do some operations on the image itself. We will need to have some models, something about physics to understand the process. We have some background information, like for example these annotated images. This allows us to estimate something about the object. So we'll know something about location and geometry. This is mainly Photogrammetry II. The type of object we will cover in Photogrammetry I. Knowing something about the camera is also something we will do in Photogrammetry I course. So all the different tasks that we're actually doing can be seen on that slide. We actually start with processing images, and then actually move in this direction. The different tasks which are important, like object localization. That means we know that there is an object, we know its class, but we want to estimate its position. So we want to localize an object, determine the pose or the position of an object. Or object reconstruction. That means we know there is an object, we know which class it is, we often also know where it is, but what we want to compute is actually the 3D shape, the geometry. And this way we can actually go through all the individual parts, and of course, the more things I need to estimate, typically the more tricky the things actually can get. But all those problems are actually interdependent. So if I have one given, it may make a different estimation process easier or more tricky. In terms of the cameras, there are two estimates. One is what's called camera calibration. That means we want to estimate the so-called intrinsic parameters of the camera. For example, what is the focal length of my camera? What's the size of a pixel? How far is the pixel away from this pinhole? And is there any distortion in the mapping, for example, from my lens? That's something which is called camera calibration. That means we typically know or often know where the camera is, but we want to estimate those intrinsic parameters to get a better mapping. So describe this mapping, how to go from that object to that image plane more accurately. Or we want to estimate the camera. Often the intrinsics are given. We want to estimate where those camera is. So I have a calibrated camera. I take an image of the scene here, and I want to later on estimate where this camera is in the scene. Of course, we may also want to estimate both of the things at the same point in time. Then I need some additional background knowledge. We can also, to understand the mapping process or to motivate some of the things here a little bit better, if we look to the key of human perception. That means we have a 3D object in the world. We use our eyes, our biological cameras, to observe the scene. This goes to our brain. Our brain does something magic with it, and we get an actually interpretation out. So this is kind of the basic cue of processing. So we use our cameras, and then we actually process this information. The question is, who does most of the work? The eye or the brain? What's the more tricky task? What do you think? Who thinks the eye does most of the work? Who thinks the brain does most of the work? That's pretty good. Okay, so we can actually make an experiment to actually prove that. So we can take a person who's blind from birth on, so this person has never perceived the world through its eyes, through its biological sensors. Then we take a video camera which records a scene, say with a very small resolution, let's say whatever, 50 by 50 pixels. And what we then do is actually take a small printer like a braille display blind people can use for reading, and we actually project this image, for example, on the back of the person or on the arm, just by kind of stimulating the skin where a pixel is. Actually, the people can actually see with this process. So the person can actually perceive the scene, understand what they see, what is in front of them, just by using their skin as kind of an alternative to using their eyes. We can actually show that the person can recognize, for example, different objects or interpret the scene, but with very little training. And this actually shows that the eyes, although they're very, very good cameras, and the cameras that we have nowadays, at least in most of the cases, cannot compete with our eyes, there's still the brain does most of the work. And this is also one reason why algorithms are so central in photogrammetry, because we have cameras, we have images, but the difficult task is often not obtaining those images, but actually making sense of those images. So developing algorithms which can, for example, interpret those images. This is a very central point in here. So what are typical sensors that we use in here? One of the things is actually what you see here is what's called Microsoft UltraCam. It's a very, very nice, very heavy, very expensive camera that you put on an airplane and you fly over the Earth. You take aerial images. And this is actually the system which was used to create Bing maps. So exactly those cameras over here. And this is kind of the very, very modern version of actually the guy there sitting in the back where I point with the laser pointer. So this is the kind of 200 years old, 150 years old version of that, using these large film rolls for taking aerial images. And this is kind of the very, very modern variant of that. This actually generates images using different channels, panchromatic as well as color, near-infrared information is all, you get high-resolution images from that. There are also line sensors, which just scan a single line. We can actually fly over that, and then by stitching line to line, if I know the position of the airplane of the camera, I can actually generate those images of the scene. If I go to applications on Earth, we have these typical cameras like these ones over here. So these are just standard cameras, approximately this size, industrial cameras, used for different types of applications, and where we can observe objects, measure objects. And actually also nowadays consumer cameras, actually pretty good cameras. So if we calibrate those cameras, we can actually use those cameras as well to get high quality image material and do measuring processes with really standard cameras. There are additional sensors, like for example laser rangefinders. These are just 3 examples. So this is a scanner which is used, generates very slowly but highly accurate 3D scans. So if you look into laser data processing here, especially at Heiner Kuhlmann's group, you will work with data coming from a sensor similar to this one. This is a 2D laser scanner, typically originally used for security applications, but also kind of standard line scanners today. And this is actually a Velodyne scanner. So this is one of those scanners that most of the autonomous cars actually use today, or modern variants of this. This was actually the first one over here. Which brings me to the next block of applications. So what can I actually do with all those things? The first thing is actually we can actually generate maps. Not that surprisingly. So we can actually fly over a scene, record data, do some of the annotations manually, do some of the annotations automatically, and obtain maps. And we may also overlay those maps with those aerial images in order to actually use this for various numbers of applications. So these are just 2 screenshots from Google Maps, but they basically use exactly these processes. We have aerial images, and we can actually overlay those images with maps that we have and get information out and provide large numbers of different services, starting from routing applications, how to go from A to B, where I need to have that map, to a large number of other techniques. We can also use this to actually build 3D terrain models. We can actually fly over a scene and use, for example, laser scanners or other scanning devices to actually generate a dense 3D reconstruction of the scene and use this for analyzing the terrain using different sensing modalities. We can also use, as I said, small flying vehicles like this drone over here to actually monitor land, especially monitor farmland. There are quite some applications on this, especially if we look into not only the visible light, but also different channels in the infrared spectrum. We can actually obtain information about the health of those plants, actually generate actually maps of farmland, telling me something, what kind of crop is actually growing there, and if the crop is healthy or if it is sick. We're also here in Bonn working on those systems. So this is one of the DFG research units, which is located here in Bonn, involving different groups. Here in the geodesy department, Heiner Kuhlmann, Lutz Blümer's group, myself, as well as people from the computer science department and from TU Munich. You actually see here, this is actually Frankenforst, one of the places owned by the university on the other side of the Rhine, close to Königswinter. You actually see this drone over here and estimating the trajectory of this drone at this point in time only using GPS information, but we can actually also use camera information. So you have here actually 4 cameras, fisheye cameras, 2 looking to the front, 2 looking to the back, so stereo cameras. So look as a high resolution color camera. And we can actually use this to track the position of the platform. We can actually find those distinct points, or some of those features I was telling, track how they move in those images, and using this to compute something which is called visual odometry, or visuelle Odometrie in German, which is basically how does the camera move through this scene. And so we can actually estimate, so the blue one here is a GPS estimate, and the yellow one is the visual odometry. And even if we kind of switch off the GPS or GPS fails, we can actually use the visual odometry information to actually estimate the position of the platform over here. So we'll see that, so GPS is lost. You see only the movement generated by the visual odometry. And if you then later on reactivate the GPS, you can actually see that they start at very nearby, so there's a very small drift between the estimate of the cameras and the GPS information. Of course, the longer you actually continue, so you can see that here, actually recovered. You can actually see, what you can actually see here is that, of course, the cameras will drift over time. So if the GPS is off for half an hour, your camera estimate is likely to drift away. But we can actually estimate those things. And once we have those estimates, we can actually then use that to build maps of the environment. So we can here fly near to that building and then estimate distinct points, estimate correspondences between different images that we actually record, and then can estimate, given the platform was at point T1 here, at point T2 over here, observing my computer, we can actually estimate where that is. And we're extracting features and then doing something which is called bundle adjustment or Bündelausgleichung in German, which I introduced before, when I can actually estimate where are those points in the 3D world. We can actually show that those points are actually highly accurate, lying actually on the surface of the building. And using this for building online maps with those flying platforms, and so estimating at the same point in time a 3D reconstruction as well as the location or the trajectory of that flying object. So you can actually see here that most of the points are actually quite accurately aligned on this surface. Other things we can do actually autophotos. So this is a special type of aerial image data which is corrected so that actually we can actually measure in those images. And we can, if we have those autophotos and we know a reference distance over here, we can actually measure those distances and use this to build maps. Another application for 3D reconstruction is actually city mapping. So this is a company called Geoautomation in the Netherlands. It's actually a spin-off of KU Leuven, one of the famous universities in Belgium. And what the service they are actually basically offering is they have a survey vehicle. You see parts of the survey vehicle here, 8 cameras attached to the scene, and they drive through the scene, estimate 3D points from those images, look for correspondences in those images, and then actually generate 3D point clouds. And actually you can move a little bit further in the video. You can actually see how the car moves. So these are the locations of those cameras on the car, and you can actually build a 3D reconstruction not only of a suburb but actually up to city scale, or even larger scales using these techniques. And this all boils down in the end to a very large least squares problem that you have to solve. So estimating at the same point in time the location of all the 3D points and the location of this vehicle, you can actually overlay this with maps and actually build highly precise maps using this technique. Another example is actually 3D city models. So this was a quite early work, just driving with cameras and a laser scanner through, I think that must be Berkeley, and building 3D objects of those scenes. Of course, here some the roofs are mapped as well here, so you can't do that from the ground. So the combination of different models, and you can actually turn that into something which you now can actually also use, for example, as a service by Google, using the 3D city models, which you actually build with similar techniques. Of course, you can also use this as CAD models you can introduce to a system, but you can actually build this online as well. Other applications are, for example, the preservation of cultural heritage. So there are a couple of applications. What you see here are actually the catacombs, or one catacomb under Rome, Santa Priscilla catacomb, and you can actually build robots which actually drive through those catacombs and actually build 3D reconstructions of the scene. You can see the platform. That's actually the platform we have upstairs here, which is equipped here with kind of 7 cameras, which sit here on the arc, so a lot of light source because it's dark in there. So we need to bring our own light sources. And can actually drive with this platform through those catacombs. Images are a bit dark, sorry for that. And actually build 3D reconstruction and use this for digital preservation of cultural heritage and allowing archaeologists actually to observe those models and see for structural problems of those catacombs. We can then actually use this to build this kind of 2D maps. So this is one of the explore trajectories that we generated in one of those examples. Overlay them with, for example, aerial image data. Combine this visually obtained data using, for example, 3D laser scanners where we get a more accurate 3D reconstruction of those catacombs. But this is actually more costly to bring those devices, pretty expensive devices, a lot of manual work into those sites. These are all different applications that we can actually find here. There are also kind of some medical applications. So for example, we need to analyze those images, finding correspondences between different points in times, for example, for aligning MRI scans. You can actually use this in dentistry to estimate the root channel. If you have a root channel canal preparation, so your teeth needs fixing, you can actually use X-ray images and analyze those X-ray images to get the right instruments to actually do your surgery. You can use all these techniques for quality control. For example, you have this arm with high precision measurement devices. You can actually move that over a car to do quality control. Or other applications for that are robotics applications. So like autonomous cars. So this is actually the Google car. You have automatic lawnmowers. You have small hoovers. And this, for example, one of those examples. At that point in time was a prototype of the Samsung Hudson hoover. And this one actually uses techniques for, there's small cameras in here. It estimates objects on the ceiling and uses those estimated locations in order to localize and actually find his way back to his charging station so that the robot doesn't die somewhere. If it realizes its battery goes empty, it actually can go back to its charging station and recharge on its own. There are different applications. You can actually skip through some of them. This is actually some nice video, which also brings me to the end of today. This is actually the Google car, or kind of the 3-year-old version of that car. Here you see this laser range scanner. It's also equipped with cameras. And what the car basically sees with this sensor over here is this overview. So these are kind of different laser scans. You can see here, so these are the curbs of the street. You see some buildings over here. There's probably a bush, or these are bushes over here. And this is what the car just sees from the 3D point cloud. But it also needs to interpret the data using cameras, using classification approaches, so that we actually in the end up with something like this. So everything which has a box in here is actually a traffic participant. So this is, I think, a bus. We have pedestrians over here. We see people over here which are labeled. There's actually a car which is likely to cross the path of the car. Therefore, it's kind of in yellow. And so it needs to do all these interpretations and identify what are dangerous situations, what are safe situations, and use this in order to make the best possible decisions. And in order to do that, to realize those applications, we really need to know what does the environment looks like, where are we in the scene, what happens around us. And this is just a small demo from the Google car given in 2011. It's actually a parking lot, and the car driving the parking lot on the top of a parking garage. I hope you can hear that. It's a kind of nice video. So this was the first public presentation of the car. And the goal is to drive as fast as possible through these pylonen. Okay, so it goes on for quite a while. But in order to realize those applications, you actually have to go back to a lot of traditional techniques in order to estimate what happens around me, where am I, and what does the world look like. These are very central questions you have to answer for realizing all these applications. And my goal is within this course to actually introduce you to those different techniques that in the end you're actually able to understand the overall process and even build parts of these estimation processes on your own. And these are kind of key building blocks for a lot of applications. There are a couple of relevant literature for this course. Just put them on the slides. There are actually three things which are pretty important. The first one is actually the script by Wolfgang Förstner, which I mentioned before. Again, this script for Photogrammetry I, let's say 90% is identical to the course material I have. In the sense, some of the examples I actually took from the Zielinski book on computer vision. You actually also find a draft of that book online, so all these documents are actually available to you. And for the machine learning part, especially these classification approaches, I actually found the Alpayadin book an excellent technique. But in terms of the notation, I stick with Wolfgang Förstner script. So if you look to this German script, you should find the direct correspondences between what I'm telling here and what happens on the slide. So the next lecture is today in a week. So there's no lecture this Thursday. Next week we will teach on Tuesdays and Thursdays. Before we close, are there any questions from your sides? Okay, if this is not the case, thank you very much for the attention and see hopefully as many as today next week. Thank you very much.